want us to consider the scenario where the production of pipes has a mean diameter of 2 inches and a standard deviation of 0.13 inches. We're told here the shape of the distribution is approximated by a normal distribution, and I want to talk a little bit about why a normal distribution would be a reasonable thing here. So this graph here is the graph of the probability density function for a normal distribution. What we want is for the most common outcome, which is this peak, to be 2 inches to meet specification of production. And so the peak corresponds also with the average, and it's also the most likely outcome because any interval containing that peak has the most area and hence the most probability. So that's one characteristic of a normal distribution that um, would be desirable for this company. Another is that the probability that it's misspecified or misspecified by a lot is very small. So probabilities far away from 2 inches um, correspond to typically smaller areas and smaller probabilities. So for example, the further out you go to 2.2 to 2.3, that occupies less area and less probability. So it's a lower likelihood of an event having a pipe that is far from 2 inches in diameter. Okay. Um, The other thing is that this graph is symmetric. So you're not more likely to have a part that is above 2 inches versus below. So if you were more likely to produce larger parts, that would be something that's systemic in your production. And you might try and figure out why that is. So here it's equally likely that something's above 2 inches above the mean versus below it, and that's called a symmetric distribution. Okay. One thing that it would be desirable, and I'm going to talk about this in a minute, is we like smaller standard deviations. Smaller standard deviations means that we're less likely to have events um, that are far from the average of 2 inches. So the smaller the standard deviation, the more likely it is that we have parts that meet the 2-inch specification, and less likely that we have parts that are um, far from 2 inches or misproduced, misspecified. So let's explore these graphs. So here I have graphs all with means of 2, um, and the the variation or the standard deviation, remember standard deviation is the square root of variance, are all different here. So we can see the smaller variance, this blue curve, it makes it the most likely that an event occurs at 2. So smaller variance is better. A larger variance, so the green graph, makes it so that the peak is much smaller, and we can see probabilities in the tail far from 2 or far from the mean are much more likely with more variation. Okay, so variance makes uh, larger probabilities more likely. Okay, um, so that's kind of what the variance controls in the normal distribution. It controls the spread of the data, or meaning that uh, larger events or values become more probable. So here it becomes more probable with the green graph as compared to the blue that we have a part that is far away from the mean of 2. So for example, 4 or 6. 6, for example, is not very likely at all under the blue graph, but it is not unreasonable for it to occur. Excuse me, it's not unreasonable for it to occur under the green graph, but with the blue graph, it's very unlikely to occur. Okay. So let's answer this question here. So we're on to question 3. I want to calculate the probability a pipe has a diameter of less than 1.8 inches. And here, all we're going to do is we're going to use the cumulative distribution function. And we need to use the cumulative here because we're calculating a less than probability. So this shaded area, that's everything to the left of 1.8, and that's the probability of less than. That's the definition of cumulative. We can calculate this as follows with stats norm CDF, the cumulative distribution function, and it gives us about 6% probability that it's less than 1.8 inches. Okay, the next question, question 4 here, asks us to use the normal distribution to determine the probability a randomly chosen part has a diameter of 2.2 inches or more. So remember, we calculated less. What are we going to do with more? Well, if we repeat what we did before with the cumulative, this is what we calculate with the CDF. We calculate the probability of less than 2.2. That's about 93, 94% of the diameters are less than 2.2 inches. And what this corresponds to with the cumulative distribution function, it's everything less than 2.2. So how do I get the probability of greater? Well, that's the complement rule, and I just do 1 minus. So I do 1 minus, and I calculate the greater than probability, okay, right here. So let's adjust this CDF so that it's correct, 2.2, and we should get this should be 0.13. We should get the 6% there. Okay. Okay, so this shaded area corresponds to 6%. And now the next question is, what's the probability that it's between 1.8 and 2.2 inches? Well, let's remember the probabilities we calculated before. What we calculated before was everything less than 2.2, okay? And we calculated everything less than 1.8. What should I do with these two areas to get things between 1.8 and 2.2? Well, it seems if I look at this graph, this gives me everything less than 2.2. This gives me everything less than 1.8. To get the desired probability here, between 1.8 and 2.2, I just need to subtract this probability or area from this, and I get what's between it. Okay. Let me just change the standard deviation here, and this one is 0.13 as well. Okay, and I get 87% of the parts are between 1.8 inches and 2.2. Okay. Okay. So a couple of other things I just want to talk about is what happens if I change the means. So here, for all of these graphs, the variance is 1, and I've changed the mean to be -2 for the blue, 0 for the this orange, and +2 for the green. And what you should notice is that the peak of this distribution corresponds to the mean value. The second thing is that changing the mean changes the location but not the shape of the distribution. So shifting it from -2 to 0 to +2 is what these series of graphs illustrates, but they all have the same general shape because they have the same variance. So the variance adjusts the shape but not the location. Okay, and then the last thing that I wanted to mention is the cumulative distribution is defined by this formula. And I've gone through this demonstration of calculating probabilities in Python because it's not possible to anti-differentiate this improper integral. In addition, if you wanted to calculate these values that we calculate in Python, you'd have to use numerical integration with Riemann sums or like a trapezoid rule. And they'd all give you approximations, and what you get in computer is a very accurate approximation. Um, and so it becomes necessary to use some sort of numerical integration assistant through software or a calculator. So it's not possible to have a closed form antiderivative for this integral right here. Okay. We also know from calculus that this improper integral converges, which you can prove fairly easily. Okay, so that's why we've gone through all of this in Python, is because if you want to calculate these things, you need to use numerical integration, and the best way I think is in Python or using an online calculator, and the third best way would be with your calculator or your textbook, which has the table of probabilities for this.